just introduce Pilar. But before even doing this, again, like as I was saying this morning for the Alaskan volcano that Kirsten has presented, geology is a very good tool, good way to travel the world. And so after being in Alaska, now we're going to be in Costa Rica. That's where Pilar actually works as a professor at the University of Costa Rica in San Jose. Is that right?
Yes, San Jose.
And Pilar, before landing in this position, actually was PhD at Virginia Tech, right at the time toward my last years of PhD. So we overlapped there. So I actually had the pleasure to know her personally and to appreciate what a good PhD student she was. And with many ideas, a lot of passion and interest in geology and in volcanoes. Okay, so from her PhD, Pilar did a very great job that put basis for a lot of publications, some of which actually were published in a very high ranked journal, like I said to students last time. And I think this is Nature Science.
Nature Communication.
Nature Communication, exactly. And you were talking about the ocean island basalts and the signature. Yeah. Exactly. And so it is amazing on how much work she did during her PhD, during her postdoc, during now also she's doing a lot of work. And she's lucky that she's around volcanoes. And it's also important to mention that Pilar had actually many awards. Okay, and just to mention some, like best rated professor at geology department in 2016, and she had also some for who is interested in pop culture. She has also like some talks in YouTube. Am I right, Pilar? Yes.
Yeah.
And so
they're Spanish, I think, but
yeah,
you're welcome to see them.
Exactly. And anyway, I mean, like she has been amazing. Again, like the type of work she has done and the amount of work she has done. And this is like to say that, to give courage to our student group that things can happen, that you can be successful, and that you can, again, like travel the world using the rocks and studying volcanoes. Okay, so today what Pilar is going to present us is going to be about a volcano that is kind of close by to where she actually works. And the name of this volcano is Poas, that has given sign of activity even recently. And so that's what is going to be the focus of the talk. So thank you, Pilar. We no further to say.
Well, thank you very much, Rosario, for that introduction. And I'm very happy to be here with you guys, sharing some of the studies that have been made in Poas Volcano. When Rosario asked me to give this talk, I'm pretty sure he didn't know that Poas Volcano is actually my favorite volcano of them all. And I will tell you a little bit more about that in further on the presentation. And yeah, thank you so much for the invitation. And just as a comment on the introduction that Rosario made, I am very grateful for the opportunities that I have had. I still consider myself as an early career scientist. And as Rosario said, don't get discouraged at any point in your career. Like, if I could tell you how many times like I have had like closed doors, they're far more than the ones that actually opened. So I think this is a way of persistence persistence in your career. And if this is what you love, just go for it. And I'm pretty sure things will go through. And the important thing is that you love what you do. And some of the things that really caught my attention from the earlier talk with Kristen was how they achieved so many like new successes with having an NSF project funded with only female PIs. That's amazing. I was like, wow, they're setting up the bar, and that's really inspiring. And also seeing like a female head in your department and seeing so many female students, it gives me hopes. And this is really important. I think things are changing for the good. We're getting more and more women, and that people from all different backgrounds in geosciences. There's a lot of things to work on, and we're getting there. But it's inspiring. So let's talk a little bit about Poas Volcano, shall we? Actually, this picture that you see right here in the introduction slide, I took it from the visitors center at the National Park in Poas in February of 2017. And this is one of the last pictures that I took before all the crater and its morphology changed with the eruptions of 2017. So I'm actually really proud of this picture because you can see if you see the southern edge of the crater right here, where you have like a orange, like an orange tint to it. This is an old lava dome that formed back in 1953 when the Poas volcano had a series of vigorous and active eruptions. And from then to 2017, the volcano was actually pretty stable, always with fumarolic and gas activity, but no major eruptions. So from 1953 to 2017, this dome existed. And after the activity of 2017, it disappeared, sadly. So I'm going to show you later on the talk some of the changes that occurred in the crater morphology that are quite interesting. All right, so where is Poas Volcano? Where if you see Rosario's background, you can see a little pinpoint in the map, right where Poas Volcano is located. Is right in the middle of Costa Rica, and Poas is one of the other complex stratovolcanoes that are located in Costa Rica, and also located in the southern end of the Central American volcanic arc here after abbreviated as CAVA, which is a little, it's usually abbreviated like that. This is one of the most active volcanoes in Costa Rica and Central America. And here in Costa Rica, we also have other active volcanoes. Maybe you have heard of them. Rincón de la Vieja, which is in Guanacaste province. We have Arenal, which is quite famous, and it's very nice because it has like this stereotypical shape of the volcano that every little kid will draw if you ask him to draw him or her to draw a volcano. And then we also have Turrialba, which is active, and Irasu. All of them are active quite at the moment. And most of the types of manifestations that they have, there are a lot of fumaroles and a lot of phreatomagmatic explosions that are small. Are you all familiar with phreatomagmatic processes?
We have touched a little bit, just a bit.
Okay, good. So the main type of activity that Poas Volcano has shown in the past decades are phreatomagmatic type, where you get explosions that are driven by water and aquifers that get heated by the magmatic system underneath them. So even when the magmatic system is given the heat to the system, they are not actually exploding. So it's a little in-between activity, right? And they're characterized for producing a lot of ash falls or blocks and bombs that are constituted by older pieces of the volcano edifice. So they're not juvenile products, but instead parts of the crater that get eroded, fragmented, and explosively thrown out. So this is the type of activity that we will typically find in Poas Volcano. This is another picture. I took it in 2009. And as you can see from the picture that I showed you before to this one, there are not really that many changes. Even the color of the lake looks quite similar, which is funny because this volcano is known for the coloration changes that occur in the lake throughout the years. And I will show you a little video about that in further on our presentation. Well, we cannot talk of a volcano as an isolated edifice, right? Every volcano is in some sort of either arc or volcanic system accompanied with other volcanoes around it. And this is the case for Poas Volcano, which belongs to the Central American volcanic arc. And this is actually a picture of Arenal that I really wanted to put in the presentation because you can see the shape of the volcano. It's just perfect. Well, so we need to consider what is the context of Poas in this Central American volcanic arc. And one of the things that Kirsten mentioned in her talk before is that we need to ask ourselves, what is subducting? And this is also the case for Poas Volcano and the Central American volcanic arc. So I wanted to show you what's the geotectonic setting and context that we are talking about today. So in this map, you can see Costa Rica right here, Panama, and then towards the north, you have Nicaragua, Honduras, El Salvador, Guatemala. El Salvador is this one here, Guatemala, and Mexico. And as you can see, the Central American volcanic arc is pretty much a continuous arc going parallel to the Middle American Trench, which is where Caucasus plate subducts underneath, the Caribbean plate and some parts of the North American basement that are found in Guatemala up here in the north. And as you can see, the Central American volcanic arc sort of stops when you get to the limit between Guatemala and Mexico. That's because of the plate limit that exists there, where the North American plate and the Caribbean plate interacts. And this limit is a strike slip type of limit. And you have a major fold zone there, which is called the Motagua Fold Zone, coming right in the middle of Guatemala, actually. So that's what we could consider the northern boundary of the Central American volcanic arc. All the way going towards the southeast, you have a more or less continuous feature that reaches all the way down to Panama. What you can see from this sketch is that, well, you have the Caucasus plate subducting at around 73 millimeters per year, closer to Salvador, Guatemala, and Honduras. And as you go down southward, these velocity changes becomes faster to 85 millimeters per year. And there are two things that we need to consider when we talk about especially volcanism in Costa Rica and Nicaragua. And it's that towards the southeast, we have very complex interactions because the Caucasus Ridge, which is a line of seamounts that are related to the activity of the Galapagos hotspot down here in the south, comes right to the trench and starts subducting. And this changed the evolution of the geochemistry of the volcanic arc, especially when we look at Nicaragua and Costa Rica. You can see how this affects the geochemistry of the lavas that are being produced there. And so that's one thing that we need to think about. The other one is, well, you also towards Panama, you have the interaction of actually three plates, because besides Cocos and Caribe, you start having the Panama microplate, which is delimited by the Panama fracture zone that you can see down here. So it's a microplate, and it changes, right? It changes how the dynamics of these parts of the subduction zone each other. Let's see. Another thing that we need to take into account in the context of how the magnetism is occurring in Poas Volcano is how is the mantle beneath our subduction zone and beneath our arc. In this paper from 2008, Kai Hornley and collaborators from EMR, they studied how the mantle flux beneath the arc works. And they found out that generally, at least for Costa Rica and Nicaragua, you will find a flux that is runs parallel to the Middle American Trench, going towards northwest. So what this means is whatever you get subducting, say, for instance, Cocos Ridge, it interacts with your mantle wedge, right? To produce different types of melts. You subduct alteroceanic crust, you subduct, little segments, you subduct parts of the seamounts. That interacts with the mantle wedge. And in this mantle wedge, you get a flux that will run towards the northwest. And what we found, and many authors have found, is that the interaction of these subducting input can be found in the Central American volcanic arc from the Cocos Ridge towards northwestern Costa Rica and some parts of southeastern Nicaragua, which is quite interesting. And we can see that in the geochemistry of the lavas and a little bit in the geochemistry of the lavas of Poas as well. So I don't know how familiar are you guys with trace element ratios. These are like my favorites. So I'm sorry because I put this very complicated graph right here, but I'll just explain it simply, as simple as I can. There's no big secret out of these things either. So let's go back to what's subducting question. What's subducting in the Central American volcanic arc? So we see that towards the south, we get the Cocos Ridge, which is subducting. That's important. But if you go towards the north, with Cocos Plate, you start subducting a lot of sediment as well. And you can see this subducting input changing throughout the Central American volcanic arc. So In this graph that we have right here, you can see in the x-axis, we are going on the same direction as the arc. So this is distance along the volcanic front of the Central American volcanic arc. In red, you have samples from lavas from Guatemala. Then you get El Salvador. You get Northwest Nicaragua in purple closed symbols, and Southeast Nicaragua with the open symbols. Then you get North Costa Rica and Central Costa Rica. So why do we get these different symbols for sections or segments of the arc that belong to the same country, you might ask? Well, they actually show very different geochemical behaviors. And as you can see, in this ratio, barium lanthanum and uranium thorium, for instance, there are indicators of what type of subducting sediments you get. Barium lanthanum are closer to carbonate sediments. So if you get high barium lanthanum ratios, you basically are seeing higher inputs of sediments, carbonate sediments. And if you get uranium thorium high ratios, what you see is the influence of hemipelagic sediments getting into the subduction zone. So basically, these graphs show you that you have a high input of sediments going from Guatemala towards Nicaragua, and it's starting to decline from Southeast Nicaragua towards Costa Rica. This is a product of getting these Cocos Ridge being subducted at the trench. Why? Because Cocos Ridge is young. So it's a younger oceanic crust being subducted there. Since it comes from the Galapagos hotspot, it is also hotter, but overall, it will have less accumulation of sediments in time. So in this area of the trench, southeast Nicaragua to north and central Costa Rica, you start seeing a decline of this input. And that will mean, different geochemistry in the lavas of these segments of the arc. If you see the right panels, on the other hand, we have ratios of gadolinium ytterbium, cerium lead, and let's see, lead in here, isotopes. These ratios, what are showing us is the influence of the Cocos, the Cocos Ridge, which are the Galapagos hotspot tracks, being subducted and underneath Costa Rica mainly. So the main effect of these Galapagos hotspot tracks is that in the arc in Costa Rica, we start seeing these enrichments in elements that are common to OIV lavas. So gadolinium ytterbium ratios are high, cerium lead ratios are high, and also lanthanum ytterbium down here start being high at the southeastern end of the Central American volcanic arc. Same with these lead isotopes. So because hotspots are really enriched in radiogenic lead isotopes, the lavas that are deriving from these tracks being subducted underneath the mantle wedge here in Costa Rica will begin to have some imprints of these enrichments in their own geochemistry as well. So if you look at well, this is a very small map. If you look at the central volcanic arc in Costa Rica, the first volcano after the subduction of the Cocos Ridge is Turrialba. Turrialba, turns out, it has the most enrichments on lead isotopes, on lanthanum-ytterbium ratios, or cerium lead ratios as well. And this enrichment is evident towards Irazu, which is right next to Rialba, to Barba, and then to Poas in a decreasing mode. And this also is in good agreement with this mantle flux that we see beneath the Central American volcanic arc. So I don't know if you guys have some questions. If you want to ask anything, go ahead. It's okay. I'm more than happy to answer them throughout the presentation. That was basically the context for what I want to show you now. So I don't know if you have any questions regarding the subducting input, or I can just go on.
Pilar, I think let's go and see the trip to Poas Volcano, and then we can ask questions
Absolutely
related to everything. But I think it was very clear what you were saying. So
okay, I tried to keep it really simple because if you let me, I could just monologue about this all afternoon. But now let's do that. Let's focus on Poas Volcano, aka my backyard, because this, I'm sure Rosario didn't know, but I basically grew up and I was born in the slopes of Poas Volcano. And I'm from Alajuela, which is right this little yellow dot that you see here. So this is Costa Rica, and Poas Volcano is basically located around 30 kilometers from San Jose, which is the capital, and some 15 kilometers north from the town of Alajuela, which is where I'm from. It rises 2,708 meters above sea level. That is some 8,884 5 feet. So it's quite a large edifice. It's a big, complex stratovolcano, and it sits right between Barba, which is the volcano towards the southeast of Poas, and Platanar, which is on the other side. Both are dormant, so Barba and Platanar, they don't have any current activities, but there is, historical accounts that tell from both of them. Just there's no current current activities on them today. Poas is the one who has all the activity. What's interesting about Poas, which in this other little map that we have right here, you see in blue the units that belong to Poas Volcano, which is right here. Here you have Barba and Platanar. You see they're really close together. And if we take a zoom of the site where the main crater is, which is right here, you can see the main crater is accompanied by another crater called Botos, which is a little bit higher than the main crater. The main crater have been eroded and have had a lot of activity. So it's a little bit lower, but they're right next to each other. All the activity is restricted to the main crater. Botos is basically freshwater lake nowadays, and they have some ephemeral activity, but not even close to how high the activity is in the main crater. Right here we have a national park. That national park is visited for about 400,000 tourists a year. So it's one of the most visited volcanoes in the country, which also raises, it raises questions of how safe it is to visit. it is quite safe, especially or as long as you don't go when there's an active episode like 2017. So in 2017, because of the eruption, I will talk a little bit more about it in a bit. The park closed, and it has been slowly opening back to the public. So nowadays the visitors are less than they used to be, but that's just because we're taking all the precautions just to make sure it is safe. But since the big eruption of 2017, there hasn't been any other big activities there. Another interesting thing to point out here is that along the slopes, both southern and northern, we get small cinder cones and cones that are parasitic to the main edifice, as well as two lakes that are a result of maar explosions. And I don't know if you guys study maar activity.
We haven't touched on Mar.
Okay, well, I won't go too many into the details of that, but they are very shallow, very explosive volcano eruptions that usually will form a circular lake after the activity. And these two maars that are right here, one is the Rio Cuarto Maar and the other one is Ule Maar. They are both between 1 and 2,000 years old. So it's quite recent activity, quite explosive activity as well. And we now have two beautiful relic lakes to visit on vacation. But that's something that's unique to Poas. And as you can see, these centers are aligned north to south. And that's not a coincidence. What happens here is that because of all the forces, both from the convergence of subduction to the general tectonic setting of Costa Rica, what you get are tectonovolcanic fractures that are oriented north to south. So this series of cones can be seen here in Poas, but also you have cones or aligned north to south in Irasu, for instance. So it's a matter of the combined interaction between the tectonic folds and the magmatic activity from these centers, which is it's quite neat, I think. All right, so the other thing that I wanted to mention here is that the main crater is characterized by this Laguna Caliente, which is the name of the lake that sits right there in the main crater. It is a super acidic lake. It has pH values of close to 0, so they're super acidic. And it has, it has changed over the years, but usually may have a diameter of around 300 meters in shape. And Poas has been active throughout the last 200,000 years. So, all things considered and geologic time, it's quite young, Oh, yeah. So I added a little star right here. That's exactly where I'm from, which is a small town north to Alajuela. And if you see, it is actually on top of this inverse fault that marks the southern limits of the volcanic edifice. So if you sit right on my grandma's house, the thing that you have in front of you, it's a giant fault scarp, which is unnerving. But it's a beautiful place. All right. So if we take into account how these units are related to each other in temporal and spatial continuous, we can see that Poas Volcano, well, it has been constructed on top of the Central Valley basement, which have a 700,000 to 330,000 years old, more or less. And it has been constructed in what have been identified as three main phases: Proto-Poas, then Paleo-Poas, and Neo-Poas. Proto-Poas is the oldest phase of construction. That means that all these units are covered by the other two phases. So it's not very well studied, and it's not very easy to study either. So here, or at least in this map, what we see are the units from the Paleo-Poas construction period, which goes from 600,000, 700,000 to 200,000 years old. And on top of that, we have Neo-Poas that goes from 60,000 to today. So what you can see is all of these units that we have marked here are composed from lava flows, some massive lava flows that go from compositions that go from basaltic to dacitic, but also quite some units of pyroclastic flows and tuffs. So we have both effusive products as well as pyroclastic products in the mate of Poas Volcano, with the addition of all these small cinder and pyroclastic cones that you can see in the southern slopes that are a little bit young as well. So in this figure from Ruiz and collaborators in 2019, they model what will be the simplified evolution of Poas Volcano, going from 700,000 years to basically present. And they show how all these units that were mapped in the figure before have a relationship between each other, and how many different volcanic centers there have been throughout the history of the Poas Volcano edifice. Nowadays, we can see developed all of these small cones and centers, and that have helped on the construction of Poas Volcano as a whole. As you can see, the timing of this stratovolcano is quite some time, 700,000 years. But again, in the main scheme of geologic time, is actually quite recent, or at least for the scales that I'm used to think about. So I wanted to talk to you guys about a little bit of geochemistry from Poas Volcano. And so in these graphs, we have all these little symbols representing the units that we saw in the map and in the model before. They're all separated by age, or by their, if they're a lava flow, if they're some pyroclastic deposits. I'm not going to go into the details of each one, but what's interesting is that geochemically, all of these units can be described or separated between two distinct geochemical end members. One is called Sabana Redonda, which is the one with SRGC that you see here. And the other one is the von Francius geochemical component that you see down here. The difference between these two geochemical end members are that Sabana Redonda is generally a little bit more alkaline than von Francius one. So there is a how do you say it? Like a cyclicity in the resulting geochemistry of these lavas. And it's not uncommon that you get lavas that are more calcalkaline, like the von Francius end member, and followed by lavas that are calcalkaline high in potassium, like the Sabana Redonda end members. What this means is that we have a source, now two sources, that coexist in the magmatic system. And you get sometimes a flavor more like von Francius and some other times a more Sabana Redonda flavor to the lavas. And they coexist through time. But overall, the youngest products, the youngest lavas right at the summit are tend to be, you can see they tend to have both high titanium and low titanium, which means that they coexist, both end members coexist in the earliest products of Poas Volcano. And the result is that all of the units that have been mapped and recognized in Poas Volcano can be explained as a mix of these two geochemical end members. And the only thing that changes is how much of each end member, it gets mixed in each unit. Oops. Both end members and the resulting lavas show that you have a typical calc-alkaline fractionation trend in all the lavas and units that you find in Poas Volcano, going from a coexisting olivine, pyroxene, and plagioclase system to olivine plus pyroxene plus plagioclase plus magnetite system coexisting, which is typical for a calc-alkaline fractionation trend. Basically, the Sabana Redonda geochemical end member showing higher alkalinities and higher titanium, also higher zirconium, and higher lead isotopes. What's telling us it's this source is the one that's showing the most interaction with Galapagos hotspot tracks being subducted at the trench. So hence that's why it has this more alkalinity to it. So that's for the geochemistry part of the magmatic system. And I'd like also to take a time to discuss some more recent volcanic activity. See. Historically, there have been reports of activity in Poas Volcano since the early 16th century. Actually, the first reported ascents to Poas Volcano were done in the 16th century, right at the time of colonization of Costa Rica. However, the history of this activity was what's the word that I'm looking for? It was reported, more formally reported since the 1800s. So one of the first sketches of Poas, um, where one like this one on the right side from 1863, where they represented both Botos crater, a little bit more elevated, and the main crater in the northern part, having, as you can see, some fumarolic activities. Actually, these degas and fumaroles have always been present on and off, and sometimes changing in the location within the main crater, but they have been quite constant through time. Um, Historic activity dates back to at least four main volcanic eruptions. The first one was around 1834. That's one of the oldest recorded volcanic activities in Costa Rica, where some some explosions in ash columns were reported. We don't have a lot of information from this time. There's only reports of these eruptions and nothing very meticulously studied. But that began to change with time as Poas became a big interest in, for instance, some German naturalists that came to the country really early on. And that's actually why the cone that we have in the northern face of Poas is called Von Francius, which is the last name of one of these German naturalists that came to the country to study well, nature in general. So in 1910, we had another big eruption reported. Not a lot of information for that one either. But in 1953 to 1955, there were a series of eruptions that were well documented. Well, this I think I didn't add the picture from the 1953 eruption, sadly, but that's the one that not only created high, thousands of meters high columns of ash and other pyroclastic materials, but also created the lava dome that we saw in the first picture with the orange stain to it. So that's when that dome formed. From the 1950s to today, the only big eruption that we have had was the 2017 eruption, which occurred in April of 2017. Right. So I added a small video from, this comes from the National Seismological Network in Costa Rica. So I'm gonna play it. It's just a presentation of how the different how changes have happened to the main crater over the years, not only in their morphology but also in the color that we see in the lake. Oh, here I'm gonna there's some music to it. So this is a picture of the Laguna Caliente, and it is known that volume and temperature change in time. So let me get a little bit back. Basically, when there's not a lot of activity and the temperature is lower, the lake will look more green to blue with a hue like this one in the picture. But when acidity increases and when temperature increases, it begins looking like this, a little gray. And so the change in the color is basically because you get more and more gases, especially sulfur dioxide, being buffered by the lake's water. And this sulfur dioxide comes from all the active fumaroles that we can see around the crater in here. The volume of the lake can change from when we have rains and when we are in the summer. So you can see that the water will descend and go up again. So, and this is how it changed from 2016, 2017, 2018, and I think it stops in 2019. So let me go back a little bit. Oops. It goes a little fast, but you can see then that during the eruption of 2017, we completely lost the lake. It was dry, and what it meant is that the gases and all the acids that come from the activity couldn't be buffered by the lake. So that's why that could be used a little bit of a precursor of how much activity, magmatic activity, you're having in that period of time. So whenever the lake dries, you can expect an increase of phreatomagmatic and small explosions in the main crater. Right now, we have the lake back. So it's been growing since 2017. And well, this is the picture when the lake was pretty much dry. And you can see this column of gases, ashes, and other particles. Maybe if you look a little closer, you can see that it looks a little bit reddish and a little bit orangey. So in the initial phases of 2017 eruptions, what we got was the fragmentation of the dome that had that really big orange spot. So in the first periods of activity, what we got when we sampled the ashes, it was orange ashes. It was amazing. It was like that was the dome of poor dome being tear apart, all fragmented by the eruptions. This was documented by, actually, this was a photographer that was in a plane during the big eruption. And here you can see the destruction of the dome that I mentioned before. So right here, it was gone. So I think, so in the big eruption on April of 2017, the gas and ash columns reach up to 3,000 meters upwards, so 3 kilometers into the atmosphere. So it's pretty intense. And that picture from the plane, it always blows my mind. First, because it was so lucky that somebody at that moment was taking a picture of the volcano. Oh. Okay, let me go again. So yes, so this person is the author of the picture, which I found really incredible and lucky. So the activity of April of 2017 happened in a matter of weeks and the most vigorous activities. It happened in a matter of from the 14th of April to the 28th of April, more or less, with followed by weeks of then slower activity, fumaroles, small explosions, all phreatomagmatic. So here's another video. This one is from Oxicori, which is another volcanology research center in Costa Rica. And they documented how the reactivation of Poas occurred. From the prior activity, that's what you see right here, they documented an increase of fumaroles, an increase of volcanism, sulfur volcanism. As you can see, the temperature of the lake, which is usually around 20 degrees C, started to increase and reaching up to 70 to 80 degrees C right before the big eruption. So this is 7th of April, 2017, right before the eruptions. So it started with small muddy volcanoes. So that was lucky because on the 9th of April, the park closed to the public, which is very lucky. The first eruptions were phreato type of eruptions. This means that the material that came out of them, it was non-juvenile, it was old material eroded from the crater and the dome. And one of the things that we learned from these activities is that there wasn't a lot of big seismic precursors to the big eruption. So you have this increase in activity, fumarolic and the small explosions, but not a really clear seismic precursor. So this means that eruptions in Poas are unexpected, and that it's something to consider because this is a very visited national park. So these are still the manifestations prior to the big eruption. And you see the lake temperature now is at 60 degrees C. In the 13th of April, the activity starts to increase. We have the explosions are bigger. And now, oh, that was very, very quick, but the ashes, now you could see a small percentage of juvenile magmatic components. So you start to see small manifestations of the new magma that's coming up the volcano. These are some pictures of the column on the April 14th eruption. And these are the installations and infrastructure that is in the national park. So we were lucky enough that it closed before the big eruption because you see, this is one of the trails where tourists go and blocks and bombs reach those parts. So it's so big and so energetic that these blocks reach the viewing point and the building of the visitor center. So this is a before and after. Nice pictures. You see where the dome disappeared completely. And the activity goes on. I just wanted to, these are very beautiful. But overall, the main eruptions were phreatomagmatic. So we were lucky enough to sample both non-juvenile material and some juvenile bombs. And a little bit into this video, you will see one eruption that occurred at night, where you see incandescent material coming out of the crater in the later eruptions, which means that as the activity was ongoing, you were increasing the juvenile magmatic fragment fraction in the pyroclastic material. Oh, this is it. So this one had a more magmatic input to it. And some of those samples were collected by colleagues, and we were lucky enough to study them from a petrographic point of view in a paper we wrote in 2017. This one was a big one too, in April 22nd. In this particular eruption, the juvenile fragments destroyed a camera and destroyed several of the solar panels that were located in Poas Volcano, as well as the buildings of the national park. And that's where we collected some of the bombs that were juvenile and quite nice, as we will see. This was taken a couple of days after. This is one big chunk of lava that flew 400 meters from the crater. So even though generally Poas Volcano is kind of passive volcano, you can visit it and be there. So every once in a while, you have a big eruption like those. And thank you, Christine. Yeah. So the interesting part is that we got to sample both blocks and bombs, blocks that belong to the dome or most probably belong to the dome, and another one that actually seemed like a new magmatic juvenile component from these eruptions. And that's what we studied in this paper in 2017. What we found is that the blocks from the dome, they are andesitic, and they have xenocrysts of olivine that can be recognized because they show these rims of reaction where the olivine slowly changes towards orthopyroxene as it reacts with the silica of the new liquids within the conduits of the volcano. And a picture of this is here in C&D, where you can see some plagioclase phenocrysts and olivines that show this interesting rim of orthopyroxene around it. The bombs were also sampled, and they were juvenile andesites, and they have this very glassy matrix, showing us that they cool down quite quickly, possibly during these eruptions that we saw in the videos. And interestingly, there is evidence also for crystal mush fragmentation, not so much in the bombs. I think I maybe wrote it in here, but in the ashes that we collected, we could see minerals, crystals with fractures, conchoidal microfractures, and also minerals that had a cover of glass around them. showing us that there was a disruption of this crystal marsh in the magmatic chamber of Poas Volcano. And most likely, all this activity was a result of the injection of new material into the magmatic system of Poas Volcano. And just to close, I just wanted to add another very interesting feature that Poas Volcano have, and not many volcanoes in the world has it, and it is the sulfur volcanism that occurs in the crater, in the main crater. Right now, I think because of the 2017 eruptive period, a lot of these pictures, or what you see in these pictures, was lost, but it's been reported that for the 1950s eruption, before the 1950s eruptions, there were also activity like this reported. So it's very probable that in the future, Poas Volcano will have more sulfur volcanism like this that you can see here. You can see sulfur flows that go from the fumaroles towards the crater, and it's so vigorous, this activity, that even these small flows show structures like Pajoejo lavas, like the ones that you see here. I didn't add the pictures because there were so many, but also you get the equivalent of Pelé's hair, that are these long glass threads. You get the equivalent in sulfur in some of these fumaroles, which is very, very cool, very interesting. Basically, to keep it really simple, the occurrence of this elemental sulfur indicates an elevated temperature in magmatic degassing. That means that fumaroles reach over 300 degrees C. And it follows the interaction between SO2 and hydrogen from the atmosphere. This results in the precipitation of sulfur, elemental sulfur, as you see in here. There is also being reported the appearance of sulfur as spherules, so tiny little beads of sulfur floating in the lake every once in a while. And these also have been studied to try to use it as a precursor for activity and explosions. Basically, they occur when the lake reaches 50 to 70 degrees C, and there's vigorous activities in the fumaroles. So you get these sulfur spheres in the lake. This is quite interesting, I think. So with this, this is what I got for you guys today. I think I used a lot of time for this. So with that, I'll be happy to take any questions and comments. If you ever have the opportunity to go to Poas Volcano, take it. It's really, really cool.